The topic of my project is super-resolution generative adversarial network for downscaling precipitation data. The super-resolution is the task of converting a low-resolution image to its high-resolution equivalent. For example, this image has been upscaled into its 16 times magnification factor. The same technique for images can also be used for scientific data. This allows us to gather the data via some inexpensive sensors which have low accuracy and use the super-resolution algorithms to obtain the high-resolution data. The SRGAN is the first attempt to apply deep generative model for this task. It uses a loss function called perceptual loss, and it is a summation of content loss and adversarial loss. The hyperparameter alpha determines how much weight the adversarial loss will have in the perceptual loss calculation. In the original SRGAN paper, the content loss is VGG loss, and the adversarial loss enforces the generated image to lie on the same manifold as of the natural images. However, in this project, pixel-wise mean squared error has been chosen as content loss instead of the VG loss because in this case, the realism of the data matters most, not the visual similarity with the ground truth. And the diagram shows the training process of the SRGAN. So the source of the data used in this project is UC Santa Barbara's JIPS dataset, and the focus was only on South Asia region, which contains countries like Bhutan, Nepal, Bangladesh, and Myanmar. And the data contains the daily precipitation observations from 1981 to 2020. So here is a sample from the high-resolution data. We measured the performance of the SRGAN model. Peak signal-to-noise ratio and the structural similarity index have been employed. The model was trained 100 epochs with adversarial weight 10 to the power negative 6. And from these two plots, it is evident that the loss did not differ significantly for the train and validation sets. Different weights for the adversarial loss have also been tried out. And from these two plots, it can be inferred that assigning a lower weight to the adversarial loss yielded better performance. This plot shows the comparison between the low resolution data, the SRGAN generated data, and the high resolution ground truth. This table shows the performance of the model on the validation set in terms of average peak signal to noise ratio, average structural similarity index, and mean squared error. Till now, the state of the art for single image super resolution is SR3 algorithm, which is an adaptation of denoising diffusion probabilistic models for this task. However, there is a drawback. The sample generation process of this algorithm is extremely slow. In recent times, two studies have been published on faster sample generation for denoising diffusion probabilistic models. In future, these methods can be applied for resolution with denoising diffusion probabilistic models, and the result can be compared with the vanilla SR3 algorithm and see how the sample quality differs with those faster sample generation techniques. This is the end of my presentation. Thank you.